The title of this talk is Two Arithmetical Sources and Their Associated Tries. This is joint work by Valérie Berthé, Ada Cesaratto, Frédéric Paccaut, Pablo Rotondo, Brigitte Vallée, and myself, Martín.
The diversity of authors is explained in part because this work relies on notions and methods from several areas: information theory, number theory, data structure analysis, and analytic combinatorics. From information theory, we take the notion of source and entropy. From number theory, two famous partitions, Vallée and Cesaratto partitions. Among the data structures, we choose to consider tries, and finally, our main tools will be the Dirichlet generating functions and the rise method. Let us consider two arithmetical sources given by classical partitions: the Sturm source, generated by the Vallée partitions, and the Cesaratto source, generated by the Cesaratto partitions. The Sturm source produces characteristic storming words. These two partitions have zero Shannon entropy. We are going to use tries to differentiate these two sources. Since a source of zero entropy generates very little information, it is to be expected that the average depth of a trie built on words produced by such a source is larger than for a trie built on words produced by a source of positive entropy. In general, studies on the trie depth deals with sources of positive entropy H. Let us consider a trie built on n-words taken independently from a source of positive entropy H. Under these conditions, it is known that the depth of a randomly chosen branch grows asymptotically as log n divided by the entropy. But what happens if the entropy is zero? Our main result is that for the two sources we consider, the behavior can be very varied. For the Sturm source, the average depth of a trie on n-words independently drawn from it grows asymptotically as 24 divided by pi to 3/2 times square root of n, while for the Cesaratto source it grows as 3 divided pi squared times log n squared. In what follows, we will explain how these sources are built and outline the steps of the proof of this theorem. This talk is organized as follows. First, we introduce sources generated by partitions and the partitions that generate our two sources of interest, and we also find expressions for the Dirichlet generating functions of these two sources. Then, we discuss about tries, focusing on trie depth, and we present the main analytical tool, the rise method, whose application is based on the tameness of the Dirichlet generating functions. Then, we undertake the analytical study of the Dirichlet generating functions, proving their tameness and obtaining our main results. We consider words formed only by the symbols 0 and 1. We start by considering a partition in level 0 consisting only of the interval 0, 1. In order to construct the partition in level 1, we divide this interval into two intervals. The one on the left is assigned a 0, and the one on the right a 1. We continue this process for each level. That is, in order to construct the intervals in the partition in level k, we divide each interval in the level k-1 into two. The one on the left is assigned a 0, and the one on the right a 1. In this way, each number in the interval 0, 1, except for a denumerable set of numbers, is assigned a sequence of zeros and ones according to the labels given to the intervals to which it belongs in the partitions of the successive levels. For this construction to work, we need that the lengths of the intervals tend to 0 as we advance in the levels of the partitions. The probability of each prefix w is defined to be equal to the length of the interval iw corresponding to that prefix. As usual in this type of study, we consider the Dirichlet generating function defined as the sum of the pw to the s over all possible finite words w. The Sturm source is generated by the Vallée partitions, and the Sternberg source is generated by the Sternberg partitions. Both partitions are produced by taking medians. The median of two fractions, a over c and b over d, is the fraction a plus b over c plus d. The median fraction is irreducible if the two initial ones are. Let us first describe Vallée partitions. In level 0, there is only one interval having as endpoints the fractions 0 over 1 and 1 over 1. In level 1, we divide this interval by the median 1/2. At level k, we divide each interval in level k minus 1 if the denominator of the median of its endpoints does not exceed k plus 1. Otherwise, it is left untouched. Thus, the successive endpoints of the intervals in level 2 are 0, 1/3, 1/2, 2/3, and 1. In level 3, the fractions 1/4 and 3/4 are added as endpoints. However, the fraction 2/5, median of 1/3 and 1/2, will be added only from the next level on. It turns out that each level k contains all the irreducible fractions in 0, 1, with a denominator at most k plus 1. Therefore, the number of intervals in each level is asymptotically proportional to k squared. Sequences of zeros and 1 produced with the source associated with these partitions are characteristic Stallman words. In contrast, for the Sternberg source, we consider, in level k, all the intervals in level k minus 1 divided into two intervals by the median of their endpoints. Thus, in each level, we have 2 to the k intervals. Despite the difference in the number of intervals, the Shannon entropy of both sources is 0. To find an expression for the Dirichlet generating function for the Sturm source, we study the lengths of the intervals. The process of taking medians guarantees that the length of any interval is equal to the reciprocal of the product of the denominators of its endpoints. Besides, these denominators are always coprime. For Vallée partitions, two fractions a over c and b over d are consecutive at level k if each of their denominators c and d are at most k plus 1, while the sum c plus d exceeds k plus 1. The last condition is asked to ensure that the median of the fractions a over c and b over d is not present at level k. We call ck the set of pairs cd that are denominators of consecutive fractions at level k. The trick we use to rewrite the Dirichlet generating function is the following. The cardinality of the case for which cd belongs to ck is equal to the minimum between c and d. From this equality, it is possible to express the Dirichlet generating function as 1 plus 2 times a quotient of zetas. The numerator involves a double zeta, which is defined here. The denominator zeta of 2s minus 1 arises from the coprimality condition, while the numerator zeta of s minus 1 arises from the mean of cd term. The manipulation for the Sternberg source is more complex. In order to express its Dirichlet generating function, we rely on a dynamical system. We consider a transformation T called Vallée map, which generates the Sternberg partition on the x-axis. Transformation T is defined piecewise by two branches that are linear fractional transformations. We call the left branch A and the right branch B. If H equals AB, we call h to the k to the composition of k branches of T. Functions h in h to the k applied to the 0, 1 interval generate the intervals in the bk partition. Thus, it is possible to express the sum of the probabilities pw to the s for words w of length k as the sum here. This sum can be expressed as the kth power of the operator hs, that is a variant of the usual transfer operator associated with the Vallée map T. As usual, we call h star to the union of the h to the k's, and the sum over h star is the quasi-inverse of hs. The key here is the relationship between the Sternberg partition and continued fractions. This relationship translates into the induced map of the Vallée map being the Gauss map. In fact, the composition between a to the m minus 1 with b applied to x equals 1 over m plus x, which is one of the inverse branches of the Gauss map. Now, we proceed according to the principles of analytic combinatorics. If f of z is the generating series associated with the combinatorial class H, then the quasi-inverse of f of z is the generating series associated with H star. This principle is retained for operators. In this case, we use the classical identity that equates H star to A star composed B star composed A star to obtain the identity here. Operator AS corresponds to A, and operator GS corresponds to A star B. This gives us an expression for the Dirichlet generating function for the Sternberg source as the composition between the quasi-inverse of AS and the quasi-inverse of GS. We now discuss about tries, focusing on try depth, and describe how the main analytical tool, the RISE method, can be used in order to estimate its expectation. We are now in a position to explain our problem precisely. We consider a try on n words produced by a source. We make a probabilistic study of the shape of T. We focus on dn, the depth of a random branch. We want to estimate the expectation of dn. We denote by dni the depth of the branch for the ith word. The probability that dn is at least k plus 1 is expressed in terms of the pw. As you can see on the slide, this probability is the average of the probabilities that each of the branches has depth at least k plus 1. Performing the calculations in terms of the probability of the prefixes w, we arrive at this expression involving binomial powers. To find an expression for the expectation of dn, we sum up these expressions for the probability of dn being at least k plus 1 and we obtain this expression, which is an alternating sum involving the Dirichlet generating function lambda. It is easy to see that if there is some sequence of intervals in the successive levels case of the partition that decrease in length as the negative power of k, then all the moments of order at least 2 of dn are infinite. Both 1 and 2 apply to our sources. To find estimates of the mean depth, we study this alternating binomial sum, and we call PL 2L times lambda of L. Here the analytical part begins. We will use the RISE method. This method serves to estimate alternating binomial sums as long as the values PL coincide with the values of an analytic function evaluated at L. Obviously, we are interested in the L's that range from the lower limit of the sum, which is in this case A. Let psi be a lifting of PL, and let C be in between A minus 1 and A. If psi is analytic and has polynomial growth on real part of S greater than C, then the residue theorem allows us to express the sum Fn for any B in between C and A as an integral over the vertical axis real part of S equals B of ln times psi, where ln is a kernel involving the gamma function. The idea is to use the residue theorem over bigger and bigger rectangles that contain the integer indexes of the sum. When evaluating the kernels in these integers, the binomial coefficient arises, and psi gives us back the value of the map PL. This manipulation is algebraic. For this representation to be useful, psi must have some analytical properties that we express by saying that psi is tamed to the left. Let us suppose that psi has a pole C and that it has an analytic continuation to its left. If so, instead of evaluating the integral by adding the residues on the right, we do it by considering a rectangle on the left. Let us suppose that psi is indeed tamed to the left, that is, its only pole C is in a half-plane whose border is to the left of C, and on that half-plane it grows polynomially when the imaginary part of S tends to infinity. In that case, it turns out that the alternating binomial sum is asymptotically equal to the residue of ln times psi in S equals C, plus an error term of order n to the power of C minus delta, where delta is smaller than the distance from C to the border of that half-plane. We now consider the Laurent series of psi around C. The residue of the kernel Ln times psi of S at S equals C equals n to the C times a polynomial p on log n times 1 plus O 1 over n. If C is not an integer, then the polynomial p has degree d minus 1. If C is an integer, then p has degree d. Moreover, if C equals 1, then the factor 1 plus O 1 over n becomes 1. In all cases, we can determine the leading coefficient of p in terms of psi and the gamma function as shown in the slide. We want to apply this method to our problem of estimating the expectation of the depth of our tries. To this end, we study the analytical properties of the Dirichlet generating function lambda associated with the corresponding sources. The generating function, in the case of storm, involves this zeta function. From well-known properties of the zeta function, we can prove that the Dirichlet generating function has a single pole at S equals 3/2 and compute the residue. So we can estimate the residue of the kernel times S times lambda at S equals 3/2. We have that this is asymptotically equal to 24 over pi to the power of 3/2 times n to the power of 3/2. In the case of Sturm-Ruckert, we have to resort to more sophisticated tools. From previous results on transfer operators, we know that the lambda function has as its only pole a double pole at S equals 1 and is of polynomial growth in some half-plane whose border is to the left of real part of S equal to 1. Hence, we describe the behavior of S times lambda of S as S tends to 1. And as a consequence, also the behavior of gamma of minus S times lambda of S, also when S tends to 1. Therefore, by the Rice method, the residue of the kernel Ln times S times lambda of S at S equals 1 equals n times 3 divided pi squared times log n squared plus a linear function on log n. Now we apply the Rice method and get the main results on the expectation of both sources. For a storm source, the average depth of a trie of n words produced independently by the source is asymptotically as the square root of n with a constant equal to 24 over pi to the 3/2. In the case of the Sturm-Ruckert source, the corresponding mean value is as log n squared with a constant equal to 3 over pi squared. The behavior of both sources is very different and in addition is different from the behavior for a source of positive entropy. Finally, we present a trie built on words from the storm source, another one on words from the Sturm-Ruckert source, and the third is built on words produced by a Bernoulli source with p equals 1/2. Even for this small value of n, long branches are observed, much longer than in the case of positive entropy. Let's emphasize that these tries cannot be considered typical because the variance of the average depth is infinite. This work appears as the first, or one of the first, studies on sources of zero-Shannon entropy via analytic combinatorics tools. At the beginning, we mentioned that the two studied sources have zero-Shannon entropy, but there is also another type of entropy which is Renyi entropy. The Renyi entropies of the storm source and those of the Sturm-Ruckert source have been already studied in the context of number theory, and so they are known to have a similar behavior. We would like to obtain these results using analytic combinatoric methods. VLMC sources are the simplest sources where dependency from the past is unbounded. The depth of tries for a special class of VLMC sources was previously studied. What is different for us is that we would like to study an intermittent subclass of VLMC sources, as they may be tractable, and if the parameters are well chosen, they can have zero entropy. As we said earlier, the Faraday dynamical source admits the Sturm-Ruckert partitions as generating partitions, and it is known that the Faraday dynamical source has an invariant measure with infinite mass. So its fundamental probabilities and those of the Sturm-Ruckert source are not clearly related. This strongly differs from the framework of earlier works, where sources have an invariant measure that is absolutely continuous. We would like to analyze the trie depth for the finite dynamical source, a natural but probably also difficult problem. Thank you very much for your attention.